So I want to start off by just sort of acknowledging and celebrating the people, the innovators. The title is Innovation in Clay and some other natural building materials. That without the people prepared to take the risks and the innovators, and that includes the builders, the developers, but the clients and the design team, without those people willing to take that innovation, then we would all not be here really, or have any work or any professions around earth building, albeit that earth building is with us for 10,000 years. We're still innovating with it, and we need the innovators like Martin Rauch and others who really lead the way. So this is a bit of a tough gig following that presentation. So a lot of people, my colleagues at the University of Bath, have contributed to the work that I'm talking about. So basically it's a summary of some of the work that we've done, but I always like to start off in a presentation to talk about where I come from. So this is the city of Bath. Some of you have, doesn't look very inviting at the moment, very green, but this is the Roman baths in the middle of the city of Bath. I'm sure some of you have been there. And it's a very touristy city, known for its limestone buildings and for its tourists. And this is the university, which is up on the top of the hill, which looks down on the city. And I've been there since I left. I was at the University of New England for 4 years in Armadale, and I moved here at the start of 1998. And since the last 11 years, I've been director of the Centre for Innovative Construction Materials at the University of Bath, and we're sponsored by the BRE, which used to be known as the Building Research Establishment. And now we have about 60 people working that centre, but we don't all work on clay materials or natural materials. We're looking at cement, concrete alternatives, innovative concrete structures, timber engineering, and other materials as well. But my particular interest has been in what broadly called eco-materials, could be certainly clay building materials, but also bio-based building materials. So what I'm going to talk about is some of the research work we've done in relation to earthen materials, and then, because I think there's a lot of similarities and lessons to be learned from both, and often we don't use earth just in isolation, but we use it together with other building materials, to talk a little bit about some of the other work that we've done as well. So some of the work we did probably now about 8 years ago was looking at thin wall masonry. So some of you will know Kevin McCabe. He's a very famous cob builder in Devon, and this is one of the houses that he built. And it's a beautiful sort of modern vernacular house, but these cob walls are something like 900 millimeters thick. Partly, not structurally, but partly to meet the thermal requirements of the building regulations. That's a lot of material that's gone into those walls, and it takes up a lot of space as well. So we started looking at, and a very easy way of finding clay materials is simply to take unfired clay bricks from your local brick manufacturer. So these are simply unfired, or what's called green bricks, from the local manufacturer, and using unfired clay together with other materials. In this case, there's a timber frame, which is on the outside, and then this cavity here is filled with insulation. So rather than to try and do it all with the clay or the cob, to use materials appropriately. So this is unfired clay lining the inside of this sort of composite wall section. But one of the issues was this, and the innovation and research that we got involved with was making the mortar here. Because traditional earthen mortars of clay and would work fine when your walls are 300 millimeters or 200 millimeters thick, but when they're only 100 millimeters or 4 inches thick, they don't, because you haven't got the self-weight for the stability of the walls. So just a couple of slides showing the extrusion process of making these type of units. So this is a modern brick manufacturer turning out these units, which would ultimately be fired. That a traditional clay mortar will not bond these units sufficiently strong enough even for you to have a non-load bearing wall inside. If you leant against it, it would probably break. So we developed a system using sodium silicate. Now, I prefer to use materials as much as possible in their natural state, but in this case we looked at a variety of different stabilizers, and one of them that definitely didn't work was cement. So using cement-based mortars wasn't sufficient to bond these unstabilized clay bricks. but sodium silicate worked extremely effectively. It was an 8% mixture with sand and the clay that the bricks are made from. And that was able to be produced and bagged and sold as a pre-mixed mortar. This is a test that some of you may be familiar with. It's from Bulletin 5, the accelerated erosion test, spraying water onto the surface of the brick to try and get some idea of what the durability of the materials are like. And so we've done some work at the university comparing the results from this against natural erosion of materials. So you might get a result that looks something like this from a specimen subject to that water spray. And then you measure the depth of erosion and get some indication, and it's in the Earth Building Handbook, and it's in Bulletin 5. And so as a comparison, we put some natural materials exposed to the weather. This is on the roof of a 9-story building facing southwest in the prevailing weather direction, and we basically left them there, or some of them, for up to 4 years and measured the erosion depth, and just to try and get an idea of what the rate of erosion is. I agree with Jomo in the sense that, materials will decay, and that's not necessarily a problem as long as you understand the rate of decay. But if you're trying to sell this technique to someone who needs to go to a bank to get a mortgage, it's unlikely that a mortgage company is going to give you a mortgage if you say, well, the materials are going to erode away, don't worry, because they want to see some security on their investment. So understanding this is key. And as an engineer, then we like to measure things and write performance standards and specifications. This is a graph, and sorry, you probably won't be able to read the axis, but this is the number of days. It goes up to 1,600 days, and this is the cumulative rainfall, and this is the depth of erosion of the specimen. So this black line here is actually the rainfall cumulatively over just over 4 years. So you see that in Bath, we don't have a dry season. It just rains pretty much constantly throughout the year. One of the wettest months of the year is August. It doesn't rain a huge amount. I mean, it's rained less than 2.8 meters in over 4 years. So we don't have particularly high rainfall, but it's nice and steady. And these are the responses of the different materials to this natural weathering. So this is the depth. So these lines here, and as mentioned before, then some of them actually expanded, as you'd expect. The clay swelled as they got moist, and some eroded extremely quickly and failed within a matter of a few weeks. So we wanted to compare these rates of erosion against the accelerated erosion test. Also, we compared different types of material with the different aggregate types as well. So these lines represent the different soils, and I mean we confirmed what I think any good earth builder and round earth builder will know, that the shape of the aggregate is really important. So the flat gravels here and the angular gravels eroded had much better erosion resistance than the ones with the rounded pea gravel. But we also confirmed what I long suspected is that applied to unstabilized earthen materials, which all these were, is that the accelerated erosion test performance, which is rated here, so a high number's bad, a low number's good, because that's the millimeters per hour lost of material, and this is the natural rate of weathering, doesn't correlate particularly well. So the worst performing material in the accelerated erosion test is one of the best performing materials in natural weathering, and then some others that weathered very quickly naturally actually didn't do too bad in the accelerated erosion test. So in fact, the test as a predictor of performance is fairly useless. So if there's a revision to the Earth Building Handbook, then we might need to think about that one. We've done a lot of work. I start off, I'm a civil engineer, I'm a structural engineer, I'm interested in stresses and mechanical performance, but a lot of the work we've done recently has been, as in other places as well, is much more about energy performance and hydrothermal performance. So moisture buffering, the idea that the materials respond to changes in humidity and help to buffer or regulate passively the humidity levels in a building in an internal space. And these two graphs from my colleagues here, first of all, this one here, this is an isotherm. I don't know if you're familiar with that, with this kind of S-shaped curve, shows the equilibrium moisture content of a specimen as the humidity level is increased. So you would do this incrementally, increase the humidity in a chamber and wait until the weight stabilized and then increase it again, and then you go up. Typically the response is to go up and then you come back down to zero. So you get this sort of envelope and this kind of S-shaped curve. So here the words up there say, stabilizing this particular clay material with 4 and 8% cement did reduce the amount of moisture that the material absorbed as it increased humidity, but didn't stop it being a moisture buffering material. What was more significant was the type of clays, as you might expect. So this is a kaolinite clay, and this is a bentonite, a much more expansive clay. So using the type of clay minerals was really important if you want to maximize the amount of buffering. So the more humidity you absorb, the better, if moisture buffering is what you want to do. And where does the water go? Well, it absorbs onto the surface of these fine platelet clay materials. But also, if you're building material, particularly in relation to the thin brick walls and if you've got a material that its strength is dependent upon its moisture content and it's absorbing moisture, then what happens to the strength as the humidity increases? So for a variety of different bricks, then this represents the strength normalized at 65% humidity there. What happens as the humidity changes? So the strength goes up as the humidity drops below that regularized, and it drops off as it goes down fairly consistently as a percentage of the strength for these different materials. But it doesn't ever drop to an area as you get towards 100% humidity that it completely loses strength, of course, and it doesn't continue to absorb moisture, it releases it as well. There's been a lot of work and talk recently. It's the sort of fashionable area of research in concretes and binders is geopolymers, and some of you may be aware that there's a theory proposed that one of the pyramids was built of geopolymerized material and not from cut stone blocks. So again, like earth building, geopolymers are not is not a new concept. And Alistair at the university is doing this work, and I thought I'd leave those figures in there because he likes to draw or sketch, and just to try and explain geopolymers, and I'm not so there's any chemists in the room, they'll have a better idea of what these are than I will. So solid aluminosilicates are mixed together with an alkaline solution, typically sodium hydroxide, to form a geopolymer. And as a polymer, this is a non-crystalline structure. And so people have been doing this using a source of aluminosilicates such as waste materials like fly ash from coal-fired power stations. But as we move away from coal, certainly in the UK, then the source of fly ashes are decreasing. But of course, clays are also aluminosilicates. So the idea here is, can we mix together clays with alkaline solutions to form a stabilized material? So the process here is taking your materials, combining them, and mixing them together, or the so-called dissolution, and then the diffusion, and then the gel forms. So these polymers start to form over time from the mixing until you end up with a gel material and a non-crystalline structure. And we've been working with this with different clays to try and get and improve the performance as much as possible and understand it. Why are we doing this? Because not just because Alistair wants to get a PhD, but to try and find possibly alternative ways to traditional binders like cements, which are known for their high energy use, then their CO2 emissions into the atmosphere. So can we find things that might work better as a replacement, but also improve strength and fire acid resistance and durability? That's the benefits. The cons are, and part of the research is looking at the issues around the very high pH solutions that are used, and of course they don't come without consequences either. So we've been taking clay minerals, pure illites, kaolinites and montmorillonites, mixing them with sodium hydroxide solution and getting a stabilized soil material. And just moving quickly, this sort of shows the mix here. So at the moment, a laboratory scale, we're making quite small cylinders, but there's the mix, and they're cured 80 degrees centigrade to form a geopolymer material, which is no longer really earth or clay. It's changed fundamentally chemically, and it's an irreversible process. But a few people are working on this as an alternative. And so there's compression strength testing, and a very simple test is that as it worked is stick it in some water and does it fall to pieces or not. And so these are montmorillonites and illites, and some of them you might see here do some very strange and interesting things. And Alistair's coined a series of terms of talking about things turning into palm trees, into cauliflowers, and different shapes that are formed. But the successful ones are extremely successful in terms of the strength, performance, and the durability. And so that's continuing work. Now, moving away from clay, if I may, briefly, because there are parallels between some of these developments and what I've seen with earthen building materials. This is work that I've been involved in the last 10 years, a local company based in Bristol, Modcell, who have developed prefabricated straw bale panels. And the reason for doing this are very similar reasons to what we've seen about prefabricated earthen panels, as well as doing it off-site in a factory, quality control, not being delayed by weather, and not also having straw on a site. So you have a finished panel that you take to site. And we've done a lot of structural testing in our lab to try and understand the performance of these panels. And we've done fire testing as well. And we built a prototype house on campus, which led to a number of housing schemes. This is one in Leeds. So these panels are load-bearing. The panels, the straw isn't load-bearing, but the timber frame carries the load and builds up to their 3-story houses. And if needed, because the planners like it, then you can clad them in bricks as well. So that's a straw bale house clad in fired clay bricks. What's noticeable about this is that this, as far as we know, and someone might know differently, but maybe they might know better at Straw Bale Conference rather than Earth Building Conference, is we think these were the world's first commercially built houses built of straw bale, in the sense that these were built by a developer for sale to whoever wanted to buy them. So they weren't built directly for a client. And there was quite a lot of promotional work done on this, and I think they got about 400 inquiries for the 7 houses that they built. This is a CT scan, which might be used for sort of looking inside brains and things, and this is looking inside a straw bale to try and understand the orientation of the straw and how that affects the insulation properties, because people talk about straw bale having different orientations and it's better to lay it one way than the other. And in fact, really, both the advice at the moment is wrong, and then it should be laid the third way. And in fact, the least conducting way in a straw bale, this is only a small part of a bale, you can see the individual straws there, is lengthwise, not crosswise. This is the latest project associated with Modcell, and they are building these small units. They're made, structurally, they're made from, if you know, Stramit or Durawall, the compressed straw board, and so we're doing structural tests on these compressed straw which are lined with the paper. So structurally, these are formed from this material. And inside these walls are laid with clay plasters, specifically, for their aesthetics, but also for the moisture regulation buffering aspects of the material. We've also done work with hemp and lime, and I understand there are some hemp-lime buildings in Australia, sort of really developed in France, and using the shiv that's left over from the hemp fibre production and mixed together with a hydraulic lime to form a non-load bearing insulating material, as seen here being cast against a permanent liner internal formwork and then a temporary lightweight plastic forms there. This is a sort of test building that we built at the university. And one of the issues with these buildings is going back to our weather system in the UK. It's a sort of damp marine climate, as I'm sure if you know. And so drying of these materials is an issue, can be a real issue. And so people have moved away from in-situ cast to prefabrication. Before I get there, as a result of some of the initial work that was done, particularly at BRE, then a series of houses have been built using hemp-lime technology, using in-situ. But one of the issues is needing to develop a technology that really can be delivered 12 months of the year. You can't have seasonal building because you get delays in contracts and funding, etc. So if you say, well, you've missed the summer, you're going to have to wait till next spring, then you aren't going to get very far. So these processes need to be able to be delivered 12 months of the year. And so this led to prefabricated panelized construction. I've jumped one. There's a slide hiding behind this slide, unfortunately, which I haven't animated this slide. So these are panels, prefabricated panels, not unlike the straw bale panels. And these are being used on Marks and Spencer's new, this is the place where everyone in Britain buys their underwear. And they've got their plan A because there is no plan B for the planet. And so they, as a client, wanted prefabricated hemp-lime panels through there. But you know, the person behind this at the time, Lime Technology, took huge risk because they'd never delivered anything of this scale using that technology, and really were exposed to sort of real punitive damages if they didn't manage to meet the timelines of the project. So a sort of real acknowledgement of, again, an innovator. One of the things we've done at the university is look at the secondary structural benefits of encapsulating hemp lime. So typically you have a structural frame, and so the hemp lime is cast around it as insulation. It breaks your thermal bridges as well. But I thought, as we looked at the fact that by encapsulating your structural frame, you might actually get a significant structural benefit. So this stud here and the timber there has literally crushed at that point because it was surrounded by hemp lime. And so rather than buckling in failure, it's reached its sectional properties. So the capacity of that stud is about 4 times higher than if it was just designed as a stud free. And one of the projects I'm currently working on is building homes from cork. We haven't got to growing cork in the UK yet. This is imported from Portugal, and it's cork insulation and cladding is well established and used. So this is cladding grade cork, which has been, the granules have been heated and compressed to form these blocks. And working together with an architect, this is the sort of prototype small building walls, which are 500 millimeters thick of cork, is a very highly insulated building. And we've been doing structural performance testing on the cork as well, which deforms remarkably up to a point, and then there we've taken it through to failure. So I'm given the opportunity to speak again tomorrow about the use of clay specifically for humidity regulation, and this was around this European funded project, EcoC, where we looked at clay as a liner, and we did test buildings in 2 countries. So one's the UK and one's Spain. I'm pointing there when I say that, but you can tell by the weather, by the colour of the sky, which is Spain and which is the UK, comparing the two. So just a couple of slides to finish. Some of you know, and I know Peter Hickson came over to Clayfest in our summer. So EBUC was formed, which was the UK's first sort of national earth building association. We've had regional ones in Devon, for example, for cob builders. But we formed about 10 years ago, almost exactly 10 years ago, the UK, inspired by yourselves and other organisations around the world, to support and promote earth building in the UK. And we developed further in 2015 by incorporating with Ireland, and also became a registered charity, which helped enormously. I'm also working together, and some of you will know Professor Venkatarama Reddy in Indian Institute of Science, and we're putting together a symposium on earthen structures in Bangalore next year in August. So if you fancy a trip to India, there's still time to get your abstracts in. and I've got some leaflets with me if anyone is interested. So thank you for your attention, and happy to answer any questions.